Hello, everyone, and welcome to APS webinars. Before we get started, I want to remind you all that if you want to hear about other APS webinars, to please sign up for our mailing list. You can sign up by visiting the URL that's visible on your screen, www.aps.org/careers/guidance/webinars. The title of today's presentation is How to Be Successful in a Physics Career, Preparing for Life After Your Physics Degree. I'm Crystal Bailey, and I'll be your host for today's broadcast. Thank you all so much for joining us. APS webinars are brought to you as a service of the American Physical Society, connecting you with the expertise of individuals who can offer insight into physics careers, educational programs, and professional development for students, working physicists, and educators. Today's webinar is being recorded, and everyone who registered will receive a link to the recording. Please allow us about 24 hours to send that out. After our speakers finish the presentation, the remainder of the program will belong to you for our question and answer session. Because of the number of people attending this webinar, we are only accepting text questions. So if you have questions during the broadcast, please ask them in the question box located on your screen, and we'll try to get to all of your questions at the end of the presentation. Lastly, we encourage you to complete the survey upon exiting so that APS webinars can improve its ability to provide you with these valuable services. And so with that, let's get started by introducing our speakers. Ann Leek is a postdoctoral researcher at the Rochester Institute of Technology, where she does physics education research, including investigating entry and success in STEM industry careers and access and equity in science learning. She has been a Fulbright Fellow exploring science education in Cameroon, West Africa, and has won grants to develop approaches for community-driven and place-based science pedagogy in Kenya. Ben Zwickl is a physics professor and education researcher at the Rochester Institute of Technology. In addition to teaching, he is involved in several NSF-funded research projects related to students' transitions from undergraduate degree programs into graduate research and STEM careers. Ben is the president-elect of the Rochester section of the Optical Society, which brings together students and professionals from academia and industry to promote optics education and learning. Ann and Ben are currently part of an NSF-funded research project focused on photonics and optics workforce education research, or POWER, and the NSF-funded ApS Pipeline network to develop strategies for integrating innovation and entrepreneurship into physics departments nationally. And with that, Ann and Ben, I will turn it over to you. Take it away.
All right, thank you. I'm Ben Zwickl.
Hi, I'm Ann Leek.
Yeah, and we thank you all for attending today. So students and whoever else is out there, we're glad you're here. So I got these two images up on the screen. On the left side is a tree, right? And that's meant to kind of represent an undergraduate kind of in the middle of their studies, very deep in subjects like electricity and magnetism and learning all the mathematical methods. And you know, the picture on the right is a tree in a forest, right? And so that tree ultimately gets connected as part of a larger ecosystem. In kind of a metaphor, that's supposed to represent how you take all the things you do as an undergraduate, where you're diving so deep into particular topics in physics, and then relate it to the world of opportunities that comes next. And so we wanted to kick it off with a question. So Ann.
Yeah, so when you're in that forest, the first thing we want to ask you actually is what would you see yourself doing in 5 years? Where are you going through this forest? So if you look on your right, you're gonna, or on wherever your panel is, there's a questions panel. And instead of typing a question, I want you to just type what you see yourself doing in 5 years. Because if you're using GPS or something, and the first thing you need to put in is where you're going. So let's start to see some responses. Just take a minute and think about any ideas you might have. Just throw them in that window. Awesome. I see some faculty, teaching, got a postdoc, another one like me, love it. Industry, working towards a PhD. Ooh, solar cell technology, that looks fun. Got some people going to grad school, software developer. No idea, also a valid response. I like it. Let's see, some private sector, industry folks. Ooh, teaching science communication. Anywhere there's a job, also useful. Research, So we have a lot of diverse paths that we can take as physicists. And that's something to keep in mind, is that physics bachelors, when you get your physics bachelor's degree, you're not all going to go on to faculty. Yes, some of us will, and some of us go to grad school, but actually over 40% are going straight into employment after graduation. And it can really vary what that employment looks like. So even with a physics degree, my job title might be engineer. So like a lot of people go on into engineering jobs, computer information systems, other STEM type jobs. Physics and astronomy is actually just under 5% of those jobs. And then there's non-STEM jobs that we can apply our physics to. So like we really need to expand what we think of with what we can do with physics as a degree, first of all. And so the other thing that we need to figure out is where we're coming from. What does that tree look like? And where is that tree of physics? Where can it be found? So when the other question I have for you all is, what are 3 top skills that you would list if you're going towards that job that you just wrote down in the questions panel? What are 3 skills you would put on your resume that kind of explain where physics is for you and how to position that physics for the direction you're going? So like, for example, I would list, let's see, my computational skills and problem solving, and what else? Like, I'm really good at communicating science. So those are 3 things that I would like definitely list on my resume based on what I want to do. So list 3 things that you would put on your resume. Okay, I'm seeing some good ones. Let's see. I'll give you a minute to think about that. I know it's kind of tough.
Yeah, lots of problem solving, analytical skills. Yeah. Okay, yeah, some very specific ones on statistical analyses and
data analytics, math.
Oh yeah, teaching assistants can actually be a really good professional preparation.
So we have some programming, some things from specific courses that I'm seeing, like some things from data analysis to critical thinking, problem solving, patience, also very useful, grant writing, passion. So yeah, I see a lot of diversity here. And what I think that's really reflecting is there's skills that go beyond what we're learning that might be listed on your specific course syllabus and really make those connections with the rest of the forest.
Yeah, and I think kind of along those lines, it's pretty interesting that a lot of the things that people listed are things that you don't necessarily get a grade in a course. Like you don't necessarily have a course in problem solving, but it's one of those things you hope you learn as part of other courses. And so I think one framework for thinking about, what's going to be valuable in the next step is this language of 21st century skills. You've probably heard that before. It's a buzzword, but the idea is that, in the future, jobs keep changing quickly, technology keeps changing quickly. And so you need skills that are applicable as things change rapidly. And so one framework for thinking about 21st century skills is kind of these 3 big categories. The first is the technical and scientific things, right? Those are a lot of the things that people focused on, like problem solving, MATLAB, condensed matter physics skill, mathematical skill. And so a lot of those get really lumped in there. And then you have these interpersonal skills, which are really about things between people. So all the communication skills would get lumped under that category. And then this last category of intrapersonal. So notice the difference in inter versus intra. It means kind of within the person. And those are oftentimes like personal characteristics, like something like creativity, or maybe a persistence, or being able to work under pressure, right? Those are things that are also very valuable, and they might help you regardless of what you do. And yet, you're not going to get a grade for them. And so, yeah, I mean, maybe you should, right? And so, so that's a really interesting question. But yeah, so as you think about the things you're good at, right, really think about those 3 categories, because they all end up being very important. So Anne, did you want to say a little about our research?
Yeah, so we have research that focuses really in depth in optics and photonics workforce. And then we also have broader projects that look at physics intensive careers across the US. And we have some other research that looks forward and is looking at what directions the workforce is going towards in integrated photonics in the next 5-10 years. And then we're also part of the ApS Pipeline project that really focuses back on the undergraduate curriculum to integrate innovation and entrepreneurship opportunities to help prepare you for a wide range of careers.
Yeah, and so the research that we do, consists of a lot of interviews with people. So typically for each of these studies, we have interviewed graduate students, faculty advisors. We've interviewed entry-level employees who've been in the job a couple of years, and we've interviewed their managers, people who are responsible for training and human resources. And so, we've talked to a lot of different people who have a big interest in helping, students like yourself make that successful transition into like a STEM job, whether that's research or industry or something different. And, we have kind of rigorous analysis techniques. If you're familiar with qualitative research, things like thematic or semantic or structural coding. Broadly, the goals of all this research are to understand factors for success and understand how those things can be trained or learned or developed either in classroom or on the job. And so that's kind of the big picture of what we do. Yeah, so I wanted to kick off by talking about one particular factor for workplace success. So we're going to go through about 6 of them. And the first one takes me back to my undergraduate days, and it's about question asking. And I gotta admit, asking questions in class was not my favorite thing. And I noticed, there were some people who asked a lot of questions in class.
That was me.
And then there were other people like me who felt a little shy, a little reluctant to ask questions. And in my head, I think what I was thinking is that there were people who needed a lot of help and they were kind of dependent, so they would ask a lot of questions. I know, sorry. And then there were people who were independent, right? And by not asking questions, they were sort of proving that they could do it on their own, and that was great and everything. And what I've learned from the research we've done and through, several, a decade and a half more of just life experience has shown me that that is really a terrible model for thinking about question asking. And what's a much more productive model is to think about things on 2 separate axes.
Mm-hmm. So basically, one way you can think about this is someone like me who asked a lot of questions. If I did that and I was really trying to just, I guess I'd have the opposite order. Well, we'll put the first 2 in. Anyway, if I were going to ask a lot of questions, but really use it to avoid taking initiative, then that wouldn't be a really helpful use of questions. On the other hand, if I did not ask any questions and just waited for others to tell me what to do, that's not really all that helpful either.
Yeah, and finally, there are people like me who I think, unfortunately, tried to solve everything on my own, wasting time, money, and effort. Yeah, those are things that employers say to us. Those are things that managers and employees say, like, what's the problem with not asking questions? And then finally, right, you want to be in this place where you're simultaneously independent and, asking a lot of questions. So that's really all about, being curious and eager to learn new things. I mean, that's what you're demonstrating because you're trying to push your project and your role on your project ahead, right? And so you're building on the team and all the other supporting resources that exist in your company, because most companies aren't, based on a bunch of individually successful people. They're based on, the research group as a whole, or potentially the company as a whole doing well. So it really is a team effort. And so, one really interesting quote was this one. It was from a manager, and he said, when we're working with people, you have the type of people that are going to ask a million questions, and they're inquisitive, and they want to know all the minute details that go into the process. And in the long run, they tend to be some of the best opticians, these optical technicians that we've ever had. And so that question asking really is related to just, excellence on the job and just understanding. This idea that just not being afraid to speak up, right? A lot of people have the problem where if they speak up, and ask a question that identifies a gap in their knowledge, they feel it's bringing them down a rung in other people's eyes, because you're kind of admitting you don't know things. But the person went on to say, but really that's just something we value. That question asking and speaking up is something we value here, is the ability to ask a question. Right, and so, I think those are really encouraging. Those are verbatim quotes from some people we talked to, but they really speak to this idea that question asking is not about revealing ignorance, but it's about curiosity and seeking new information in the most efficient way possible.
And also on a big picture, that it's really about valuing continued learning. And I saw some of your comments on being a self-starter, being able to find answers, being motivated. Some of that is actually, the evidence for that is in asking the right questions and being inquisitive and curious and driven.
Yeah, I mean, it's actually fascinating how many processes, whether you're a nurse trying to work with a patient and trying to figure out what's going wrong, or you're like a designer and you're working with a customer, and that whole process, that design process, gets started off with questions. And so questions really are essential in a lot of professional work. So Anne.
Yes. So the next thing I want to talk to you about is problem solving. In physics, we hear about this a lot, and usually we think about it broadly, like, oh, in physics, I'm learning how to solve problems. But really what it means is those late night sessions with your textbook and a whiteboard, if you're lucky, maybe a chalkboard and some writing utensils and a lot of tired people in a room. That's kind of what it looked like when I was a physics major. But on the job, it can be a lot different. And so one of the things we've been doing in our research is trying to expand that so that when you think about problem solving, you can take what you're learning in your physics class and expand it to these more real world problems you're going to face afterwards. So one quote that really explains this is from a physics graduate student, actually, and we looked at them as one direction you could go. Some of you were interested in graduate school. So this really gets at the difference between problem solving in your undergraduate physics courses and problem solving in graduate research. And this person said, I guess in undergrad, it's professor defined. And they kind of tell you, this is the problem you need to solve. And this is kind of the solution you're looking for. Whereas in graduate school, you have to figure out what you really want to pull out of the data and where it's going, and if what you've got is actually good or not. And so in these more open-ended problems that you might face in research, you actually have to figure out what the problem is, what you're going to do, and then evaluate your result. So it changes what you think about as problem solving.
Yeah, so I mean, one quick example that came up in some of the examples from research and graduate students was in the process of analyzing data. So the context for the problem-solving activity was analyzing data. And the particular challenge these graduate students were having was interpreting the results, right? And not only interpreting the results, but it was assessing the quality. So how do I know if this is good enough to make the claim I need, maybe to publish this paper or maybe for my dissertation? And one of the features of that that made it difficult was that oftentimes in this research setting, the outcome was unknown, right? And so, they were really, blazing a new trail, and they were finding out new things. And so they couldn't just, compare against the result from the textbook, right? That you would in an undergraduate lab, like sometimes. And so, in this kind of situation, which could be in graduate research or undergraduate research, or even in certain lab settings, lab courses, you have this very interesting form of problem solving.
In another example, if you're in like an experimental physics lab in, let's say, graduate school or in industry, another problem activity that you might be faced with is troubleshooting equipment. And in the lab, you might have like a lab technician come in, or the professor or a TA, and you can say, all right, mine's broken, I need help here. But if you're on the job, and this gets at a question that just came up actually, you might need to solve your problem with some trial and error, reading on your own. And if you don't have experience troubleshooting the lab equipment, or you don't have the confidence to do that, or even with back to the question asking, you don't know what questions to ask, then that can become a problem that you're trying to solve in your research.
Yeah, I would also make an appeal for every student who has ever been in a physics lab course and something didn't work right, and it felt like the most frustrating waste of time.
That's where the learning.
Yeah, that actually is an opportunity to do an incredibly authentic investigation. And I know it may not feel like that at the time, but you have this situation where it's not maybe clear to you what's going wrong. might not be clear to the professor what's going wrong. And so this opportunity to actually, through a systematic process of inquiry, figure out what the trouble was, the root cause of the problem, and then to think of strategies to solve it or fix it and to come to a resolution is something that has come up a lot in interviews with industry. And I think anyone that does experimental physics research would relate to that as well. So yeah, so the next thing we've been looking at is actually what does math look like on the job? There's a picture of one of our favorites in physics, Einstein, at the chalkboard, or nowadays at the whiteboard or the glass board. It's full of just beautiful equations. And I remember kind of drooling over equations like that, being like, I want to understand that. I want to be able to, fill up a whiteboard like that. And so the question is that really like professional math? I mean, clearly for Einstein, as a theoretical physicist, it was. But if we think a little more broadly about professional math use for physics, at least in the industry span of things, we actually found a very diverse range of examples of math use. And so what we might say Einstein was doing at the whiteboard was a form of modeling. So that's the yellow. And so, that could be, affecting with a particular theory, applying it to a particular real world system, and understanding how certain aspects of that system, affect the behavior of the system. And so that's the kind of thing we would do in physics a lot. And that does occur in industry for sure. However, we also see other kinds of things like maximizing efficiency, where there's a lot of optimization problems that we're doing. I don't remember doing many optimization problems as an undergrad, but the idea that if you're going to make money off something, you need to do it efficiently. And so you need to lower costs, you need to increase reliability or increase safety. And so in some form, you're oftentimes, maximizing efficiency. And so there were these various forms of math use, some of which, would look kind of like Einstein at the whiteboard or the chalkboard, but others look, very different. So one of the one physics major that we had talked to that was now in industry said, my biggest piece of advice is to learn the numerical and computational methods. Do it because otherwise you can't contribute. Yes, you're great at physics, and yes, you have a good intuitive understanding, but without being able to actually model things in real life, they're meaning the complexity that you need to use the computational methods for, right? So without being able to model things in real life, it's impossible to. It's not impossible to contribute, but you're going to be much more effective. I think that's something that has been my advice, and I've told many physics majors. So this person was very passionate about that. And so for this student who actually went straight into industry, did not pursue graduate school. Those computational and numerical skills were some of the most essential things that helped the student land their job and then be successful in it. And so they were rightly passionate. And that advice for mathematics and computational training is true for those people pursuing research and PhDs as well. And then in terms of what does computational tools look like, Anne?
Yeah, so sometimes computation can look like coding, but in other cases, it's actually using Excel. I mean, a lot of companies we talk to still rely on Excel as a tool. And so what they do is they make a macro in Excel with some of their formulas, and it actually gets shared. So it's a communication tool as well with other people who are working on the same project, sometimes going from department to department. And then some people will only interface with the macro to use it for calculations. Other people will actually design it. Other tools that were really commonly used in industry are MATLAB, Mathematica. So you probably are using those in some of your classes. They are going to come back and be useful someday. So keep up the good work. Python and R. Python is used in a lot of the different companies as a language because it's common across different disciplines, so it can translate really well in the workplace. And then there's some specialized modeling tools based on what you're actually designing. So in our optics work, there was a lot of use of Code 5 or COMSOL. So that can be like more specialized modeling tools. But if you have experience with even just one of these, then you know what it can do, so it can help you learn other tools as well. So I would say just try to get some experience with even just one computational tool that you can feel comfortable with and know what its possibilities are, and then really, you know, be willing to dig through online and find out, you know, more about other tools or what you could do with other tools that you learn as you learn them.
Yeah, and if you are already, you know, feeling proficient at programming, don't look down on Excel, because it turns out Excel, like Anne mentioned, it's this really broadly used tool, and so it's not just a means to do math, but it's a means to communicate with coworkers and collaborators, and so you know, that's part of the value. So one of the other places where math shows up a lot is not at the whiteboard, but actually when working with data, right? You might have seen jobs in data science. It's kind of a hot topic now, but certainly things involving research. A lot of research involves data, and engineers are all the time working with real devices with real performance characteristics, and there's all kinds of measurement going on. And so, you know, even this astronomy grad student said, you know, what do we mostly do is analyze images, but also fitting functions to spectra, for example. What I have to do is write a code that fits these kinds of functions to my signal, and then I have to get some parameters out of the fit. And that kind of analysis and analytical techniques, you know, is very broadly applicable. And there's far more math related to data analysis in the workplace and measurement, you know, than there is, you know, just at a whiteboard. In part because, you know, the kinds of math people express on whiteboards oftentimes is so technical and specialized. It's hard to, you know, relate it to other people unless they're kind of a like-minded expert. All right, so here's our next factor.
Yeah, so the next thing I want to talk about is design. And here's a quote from some physics students about design. Well, I guess that's more of an engineering thing. And this was a quote we've actually heard several times. But what's interesting is when you get into the workplace, it's kind of the opposite. So what are your thoughts about design as a physics thing, not just an engineering thing?
You want them to go ahead and type in
Yeah, you can
box?
type in some thoughts, or even just think about it. Share it with your computer or your neighbor. So basically, like, you know, when I think of design, I think it's pretty broadly used in physics. I think I'm getting some ideas here about designing instrumentation is really valuable for physics. Designing experiments, improving designs. It helps frame problems. Yeah, so it can be experiments. It can also be, for theoretical physics, it can be designing models, designing, you know, a tool that you can then use to do other modeling or other experiments, designing a new approach to problem solving or projects. So design is actually really important in physics, and we find it in a lot of the workplaces, but it's not, you know, it's got a lot in the process. So I'll let Ben talk a little more about the design process and what that could look like in physics.
So if you look up, you know, design process or design thinking with Google, you'll find a lot of different models for it. This is just one from a robotics curriculum. I liked it because they had a bunch of very short kind of one-word stages to this. And it kind of starts at the top with, you know, you're trying to understand the problem, and so you do some exploration of the factors, and you actually have to define the problem. So a lot of real world problems, you know, no one tells you this is what I need you to calculate. Like
my professor told me that.
Well, I know that's the way a lot of like back of the chapter problems are framed, but that's not the way a lot of problems are. They're like, well, we need a thing that does this, and the question is, well, how good does it need to do that, and what are the constraints and things that it might be under. So ideate is just sort of like a generation of ideas, different concepts that might meet the solution. You build prototypes, or you identify some prototypes. You choose among the prototypes. You do some refining, and ultimately it's an iterative process. I mean, this fact that it's a circle is a little too simplistic, but the idea that there is a fairly systematic process that you can go about for designing all kinds of things, and in terms of, you know, seeing that in terms of the curriculum, you know, we thought of a few different ways.
Mm-hmm. So you can design experiments, like some of you mentioned, and design new and different ways to do those experiments. And some of those experiments are actually used to test things. In clubs, we actually design things all the time. I don't know what clubs you all are involved in. I was involved in Engineers Without Borders, and we designed water systems. And we had a whole bunch of physicists on the team who were designing, you know, water flow systems and how to make the tap work right. And we were improving designs, and right on the job improving designs. We design with software, we design software. If you've ever played Minecraft, that is a lot of design that you can leverage in your daily life and your career.
Especially if you're making a mod for Minecraft. So. And
finally, in your community and hobbies, you design things all the time when you're cooking, baking, figuring out where you're gonna go and the best way to get there. You're designing a path. You're designing improvements to your community.
Yeah, I mean, one example I thought of, there's a terrible intersection that you have to cross to get to the public library, and there's like an interstate on one side and a busy intersection just like a short walk away. And I think it really limits access. And I would love to see some sort of like systematic design study where you think like, how could we make that intersection safer to make my community a better place so that we can use the library? Yeah, and it's the kind of thing where it's an everyday problem, but the design process can really help.
So I think this one quote from a manager really explains a little bit more about the design and why it's so important. This manager says, having a real good hands-on type attitude and mindset, the type of people that are most successful here are the ones that don't want to just sit in the cubicle all day. They want to design something and get it built and touch it and fix it because it may not work the first time, and understand the whole design process. So even if you're working as a part of this larger team and you're the one person at the computer, you really have to have an appreciation and an understanding for the design process and maybe how that one piece fits in or how you're going to use design in your job.
Yeah, one really interesting question we just got, there was a person that says, like, how would you sell your Minecraft experience as a practical experience? Yes, it's design, but I have a feeling employers won't see it that way. So I guess in my head, what I was thinking is I know there's a lot of opportunities to actually get involved in programming and by developing mods for Minecraft. And so it's the kind of thing where the process of trying to get a mod to do something, you have a goal in mind, right? I want the mod to behave like this, and you're going through an iterative series of using the programming tools. They could be Java, they could be Python, they could be some other language, to get it to work, right? That systematic design process for software, might be very applicable to a more workplace relevant thing. So I think you're right that they might not see like sitting around playing Minecraft super helpful, but if you're involved in it's the mindset of potentially wanting to modify it's like the maker movement where it's all about like tinkering and modifying and kind of a big deal. So the next factor for success, right? A bunch of people mentioned communication when we asked them, and what skills would you leverage for getting a job? And I wanted you to just, I guess go ahead, type into the box, the question box, what makes a great communicator? What examples come to mind? And we'll give people a couple minutes, and I'll read out loud some of the.
I like that listening was the first one that came up.
Yeah, definitely listening. Yeah, catering your language to different audiences. Yeah. All right, contextual jokes. Yeah, using humor, body language. Yeah, for sure. Body language is something that comes up huge in an interview.
You can really tell from our webinar, right?
Yeah, what's our body language? Yeah. Yeah, cool. Confidence, good writing skills.
Knowing your audience, understanding where they're coming from.
I think, charisma. I like that one. Understanding diverse cultures, right? I mean, so many good examples here. I wanted to share a couple of things that came to mind. So this is a picture of Richard Fineman, I think, giving some of the Fineman lectures. I thought like a really clear exposition of ideas and just laying it all out there in such a logical way. That was one thing I always esteemed, at least as a student, as being really good communication skills. Some other ones that I was aware of, right? There's all kinds of focus on scientists being better communicators to the public, whether that's young kids with Bill Nye, whether that's TED Talks talking to the general public, or going to Barnes and Noble or Amazon and getting the latest pop science book. I think like those all represent different ways to communicate to the public. But I think, like a lot of you could be very broad, right? And so some of the ones that have been very important for us in the workplace have been these additional ones, right? So engineers working in industry oftentimes have to interface with clients, right? They are, ultimately designing a product, maybe for a, one particular client, or maybe they're fulfilling a small role as part of a larger project. But either way, there is a particular client who needs particular things. You might have interdisciplinary collaborators, right? That could be true in industry or academia. We've got people that they're really good at different things, and they need to work together. And so you can't just go in there with all your, assuming that they know every single physics concept, and you better hope they don't assume you understand every single biology concept, right? You want to find some common ground and work together. Oftentimes managers or advisors, right? There'll be people that have the big picture of what the company is doing, but they don't want to know all your particular details.
And they really don't want long emails with all your particular details.
Yeah, they don't want long emails. They don't want long meetings with you. Typically, they just kind of want short summaries. And then coworkers with different expertise. And that could be, we'll go over an example of that next.
So one of the main things we've learned from our communication and what we've learned about communicating in the workplace is the challenges that come from communicating with between people that work in different areas in the same company. So like a designer working with someone who's making the product, or someone in the testing division who's working with the designer. And so it's these cross-occupational communications that are really the most challenging. And what's interesting as physicists is we mostly get the opportunity to talk to other physicists, which is great, but it doesn't really help prepare you for the workplace. So in this quote, one of the big things is to communicate with those who do not necessarily understand all of the physics behind what they're doing. So like I was saying, the makers with the modelers and designers, if you can practice communicating your physics with other people who actually don't do the same physics or don't do physics at all, that's going to give you some really valuable communication skills that you can then apply in the workplace.
Yeah, and another example kind of along those lines comes from working with clients. In this case, needing to do presentations with clients. Presentation is huge. You can know all the right things, but if you don't know how to read that information in a clear, easy to read and understandable way, you're just going to confuse the customer, right? So working with a customer is not about showing that you're a genius and that you know everything. It really is about making them feel like their needs have been understood and that you're really designing this product as an engineer in a way that works for them. And so I think big picture for all this communication stuff is that communication is much more than communicating with other technical experts or potentially with the general public, right? There's a lot of people who will be potential future coworkers or collaborators who will not have the same technical expertise as you. They'll have different expertises and different jobs and responsibilities, and really communication is about being able to take your physics knowledge or whatever you're doing at a level that kind of meets them so you can get the job done. So lastly, we wanted to wrap up with this theme.
So the other thing that we've been noticing from a lot of our interviews is that learning doesn't really stop when you start on the job. And in fact, there's a lot of technical specific learning that continues. So there's so I'm going to read this quote from a manager. Then there are intangible things that we're looking for. A lot of times it's a person's drive for their own personal development. How do I better myself? What do I need to do? They're actually pushing their learning instead of having someone have to pull it out of them, kind of thing. What books they read, why did they choose certain courses they took? It says a lot about the individual and hobbies. So what they really are looking for is your interest and ability to keep learning, because they know that you're not going to know everything for that particular job. So what they do is they try to get evidence from other classes you've taken in physics. They like physics majors because we take these difficult, challenging classes and we like it. So managers think that that's really exciting because it's evidence that we can learn and that we also have an interest in continuing our learning. And so that's something to leverage as a physicist when you go on interviews for any job, even an engineering position, is that motivation to keep learning. So you've learned this one area that you're really passionate about, and you would like to learn this other area that you're really passionate about that links up with the company you're trying to apply for.
Yeah, and I think you know, one of the things to keep in mind, and Anne did mention it, but it's this idea that jobs are incredibly diverse. The optics and photonics field that we've investigated, there are very few students that graduate with a degree in optics. I mean, there are a few programs out there, and they're great programs, but there are just very few of them. And so there's very few of the jobs actually get filled by those, you know, students from those programs. Instead, we see like mechanical engineers, chemical engineers, physics majors, and math majors like all coming together.
And actually, when you see job postings that ask for engineering students or a related field, that related field is physics, because if they just ask for physics majors, there aren't actually enough of us graduating in the US every year for a lot of smaller companies and medium-sized companies to justify a call just for physicists. So you can apply to things that say that's for engineering. You just have to make a case that you can do that job and you're interested in learning the additional aspects for that job.
Yeah, and I think, you know, the experience of that 1/3 of physics majors who go on to employment after graduation and become engineers, right? That's a pretty large fraction. And I think that's a very similar experience that they're encountering, right? They're leveraging certain skills that they knew from their physics major, and then they are also learning a lot on the job. And that happens in research. Like I thought like I had to do a PhD just to say, I thought I had to get a PhD, you know, just to keep learning. But the fact is we see a tremendous amount of learning in a lot of different occupations after graduation.
So I was just to reiterate, when you apply to those jobs, you can do those and keep learning when you get there.
Mm-hmm. Yeah.
And then, but some things are easier to continue learning than others.
Right. So although we've seen employers invest a lot in technical training, for things like communication training, interpersonal skills, we see just less training put in there. They tend to be things that they try to screen for in an interview. So, you know, all those things about body language and making eye contact and maybe asking lots of questions during an interview, right? Those kinds of interpersonal skills really do matter for finding a job. We do see attempts to provide a lot of training for that if they think you're going to move up in a leadership position. Oftentimes there's a lot of leadership training. But those intrapersonal skills, which employers might phrase as things like work ethic or diligence or honesty or motivation or curiosity, you know, those intrapersonal skills, I think employers just tend to view those as something they're not going to change, you know. So if you give the impression, you know, that you don't have good work ethic, I think they'll just kind of take that at face value and assume that they're not going to improve that. And so those intrapersonal skills are things you have to, like, you know, make shine through, you know, potentially an interview process or something. But don't worry about the technical skills, because there will a lot of times be opportunities to get training on the job. So Anne, you want to wrap us up? So
the other thing I wanted to point out is that these things aren't really separate. So when we talk to employers, they don't really see communication as separate from the physics. So like if you're trying to communicate a graph, you're not just putting the final graph up there and just sticking it on a PowerPoint and sending it out. You need to be aware of who your audience is, who you're tailoring that graph for. Why are you using that graph? What are you really trying to highlight? Because that's going to determine what colors you use, how, you know, what information you show on it. So I'm just giving you one specific example, but basically from a lot of our interviews, the companies see these things as all tied together. And so you really need to think about, as a physicist, how you've learned these things and how they really connect. And that's going to be what helps you be successful on the job and actually help you succeed in getting jobs too, is being able to tie these together.
Yeah, and I think probably along those lines, some of the richest ways to develop these skills are in places where they intersect, you know. So rather than just taking a writing course and a physics course, you know, finding opportunities where you can write about physics actually is probably a little more workplace relevant.
So with that in mind, we want to ask you to come up with 3 new skills from the ones that you typed in before that you could develop or repurpose to complement the ones you listed earlier, that especially make use of those intersecting areas like Ben just mentioned. So really think about this. We'll give you a couple of minutes and try to come up with 3 new skills that you see as really intersecting those areas that you can type into the question panel.
Yeah, okay, great. A positive attitude towards learning. Yeah, that would, I think, go a long ways towards learning on the job. Oh yeah, okay, cool. Making video animations of physics context.
I like the intersection.
Yeah, I mean, so that is showing simultaneously like communication intersecting with content,
and
maybe some programming and audience.
Public speaking, even more if you can speak about science in a public setting. Let's see, adaptation, tolerance, and confidence. I like those three.
Yeah, so that one adaptation that was mentioned, a lot of times to me, that sounds very similar to when we hear employers talk about flexibility.
Yeah.
They're looking for people that are willing to kind of, just shift their role depending on what the project needs at a given time.
They often talk about it as like wearing multiple hats, like being able to wear multiple hats. Oh yeah, tutoring middle school and high school students in physics concepts. That's a really good one because you really have to change what you're thinking about in physics to the audience and actually have an interaction. So it's not even just like you're telling them things, you're working with them.
Yeah, okay, and there's one on
analysis.
Okay, there's one on making demos of experimental devices. I think that's great. I mean, it's really showing those hands-on skills. I mean, we've talked to employers who have even said engineering students they get coming out tend to be more theoretical. And so a lot of times those hands-on skills are coming through extra work students have, or potentially like undergraduate research they have, or maybe a co-op they had, or just a hobby they had.
Yeah, like gardening.
Yeah. And so, so don't be shy about utilizing, some of your hobbies for.
Oh yeah, Photoshop skills for laboratory setups. I like that.
Yeah.
Communicating principles of experiments to business people. Nice.
Yep.
That's gonna go a long way.
Great, great.
Thank you for all the great skills, and I hope you're able to use those, either develop them or repurpose things you've already done when you're applying to these jobs.
Yeah, so lastly, we wanted to just come up with a few things that you can do. One is to kind of adapt, or at least to rethink about what you're doing as a physics major. And one is to just think about problem solving broadly. So right, you're going to encounter problems. Sometimes you might not think they're the problem you're supposed to solve, like that troubleshooting in lab, or you're programming and you've got your first programming assignment. And it's just a pain to install.
The debugging.
Yeah, it's like a pain to install the program in the first place.
Too.
And you feel like, why did they get to install it in like 5 minutes and me, I'm spending a half hour, right? But you are learning, just about how to do stuff on your own, how to seek help, how to use online message boards for things.
For question asking.
Yeah, for question asking, right? I mean, so that problem solving situation really is genuine learning, even if it doesn't feel like it. Maximize your opportunities to do computational stuff and programming. So whether that's Python, Excel, MATLAB, even if the professors don't ask you for it, you can still like, hey, what does that function look like? In lab, you can go the extra mile for some data analysis just to practice your techniques. There is an ApS Pipeline network, which I'm going to share about in the next slide, that's got stuff specifically about innovation, entrepreneurship, and career preparation. And then lastly, you can just encourage your professors and just say things like, hey, I would love it if we had some opportunities to practice presenting or writing. And I think a lot of faculty, are oftentimes eager to include those things, but kind of worried that it might seem like too big of a burden for students if it's not a communication intensive class. So I think you can have a positive impact on your department. And lastly, there's this ApS Pipeline network that is composed of several different schools right now. The goal is really to develop some curricular tools that could be adopted by other schools. And so maybe some faculty at your own institution will be able to pick this stuff up in the coming years.
And you can tell your professors to do our webinar for faculty next month.
Yeah, there'll be one for faculty next month, and also there'll be some of these Pi curriculum resources that will be available in the coming year also. And the last thing, some other things you can do, make sure to take advantage of courses in other departments, right, to complement what you're learning in physics.
And I actually, when I was a student, I got a lot of pushback for this. I had faculty come to me and say, it would be better if all you did was physics. You really should focus your time and spend more time on physics. But what's really been helping me in life is that I was a physics major, but I was also doing these other hobbies that I thought were really teaching me valuable skills. Like I was the president of a sports team and some other stuff. And it ended up teaching me really valuable leadership skills. So even if you get that negative pushback, just keep in mind that your learning is also happening outside of the classroom.
Right, which kind of goes right into the second point about, take advantage. I mean, most colleges and universities have a lot of different informal learning experiences. Maker spaces can provide a lot of community, where you can develop some, practical skills, programming skills, design skills. Internships or co-ops. There was a question that was raised earlier. A lot of students might feel they don't know what kind of job or internship they can go for. I think there's some really helpful resources that talk about common jobs that physics majors get after they graduate. And so I think starting with, fields that, basically align with those things, like perhaps data science or, some form of engineering and internship or co-op.
And the SPS and APS careers toolbox.
Yeah, we've got the link on the next slide. And lastly, when you're applying for internships and jobs, opportunities to highlight, complex projects you've worked on, like maybe it was like an end of semester project or undergraduate research, or maybe you've had a co-op. Those kinds of things really speak volumes to your ability to sort of integrate skills on a kind of a long-term project, and just keep on learning, right? It's kind of a lifelong thing.
And you're going to be ready for that in the workplace.
Yeah, and so here are the resources we're sharing. I really love those SPS Physics Career Toolbox resources. I've used those with physics majors at my own institution. AIP Statistics has lots of great data, including by state, in the United States, who's hiring physics bachelors, so you can see examples of companies. And APS Careers, right, which sponsored this talk, has a lot of good stuff. And there's also some reports that have been put out recently about physics majors. So.
And I know we're going to start the questions soon, but I just want to add to one of the questions here about research experience. Research experience, just like internships and co-ops, involve a lot of intersections of those skills. So they are really valuable experiences to talk about and to obtain. And you can start research experiences very early in your physics career, because it really gives you a chance to do some open-ended problem solving, communicate in different ways, and do a little bit more self-directed learning too. So those can also be really good opportunities. And then I guess we'll open it up more broadly to questions now.
Yes, thanks very much, Anne and Ben, for that great webinar. And, we don't have a lot of time for questions, unfortunately, at least as part of the official webinar. But we can certainly extend the discussion beyond 4 p.m. Informally for those who want to stick around. So there are a couple things there's one thing I just kind of want to comment about that you've already sort of answered a question, but I would like to add just an additional kind of perspective. Somebody asked the question of how, how do I go for a, quote, engineering job, unquote, when they're really looking for I'm a physicist and they're not looking for a, quote, physicist. This is something that comes up a lot. And I know that this aligns with what you're saying, but it comes up a lot in my experience advising students. I feel like one habit that's not very helpful is that we label ourselves with kind of this identity of slap a label on ourselves, physicist, parentheses, not engineer, or not biologist or not chemist or whatever. And I think it's really important to kind of shift our basis vectors so that we're not looking at ourselves as labeled as a subfield, acolyte or a particular kind of discipline acolyte, but rather in terms of the skills that we actually bring to the table and also the interests we have. So what I would say to that person who's sort of asking, how do I get a, quote, engineering job? I would encourage us to not think of it as a, quote, engineering job. I would encourage people to look at those careers as they require these skills, and do I have those skills? And I think as long as you're making a strong case in your resume and cover letter to that employer about having the exact skills that they're looking for, you're going to be an attractive candidate for the job.
Yeah, there were a lot of great questions on there. One that I saw that was pretty interesting that got back to some of the communication stuff. In a professional atmosphere, how helpful or harmful is criticism? I would say we have seen a lot of references to the value of collaboration. And of course, collaboration will require some level of negotiation and some level of providing, actually maybe challenging people's ideas. But I think it's very important to always keep in mind there's usually a way to frame criticism in a way that is still helpful, right? That is a way that's
and
not
respectful.
It's not personally attacking the person, but it might be just providing alternative points of view, or it might just be a simple question to help them think through their own idea even a little farther. So I think criticism in the positive, constructive way is absolutely essential.
Yes, absolutely. So we're getting a lot of questions now, which is really good. Well, so one person, getting back to the resume question just really quickly, observes that physicists make excellent engineers, and that the real challenge is kind of letting, when it comes to actually getting those jobs, letting the HR folks who are reviewing the resumes on the first cut, really helping them understand that you have those skills. And he says, make sure that your resume is tailored to the specific job posting. APS actually has a tutorial on how to write a skills-based resume based off of a specific job description. This is exactly what I tell students all the time. So I'm going to send that link out to everybody in the audience so you all have a link to that tutorial, but I think that's a really great point. So let's see. So
yeah, go ahead.
Go ahead.
Yeah, there was a question here. What if I don't want an engineering job specifically, but more about design, problem solving, data analytics, or economics requiring data analytics? I would say, for jobs that are called data science, it's actually another one of those really interesting fields where universities are starting to create degree programs called data science, but the vast number of jobs that are being filled out there are being filled from people who have a strong interest in kind of critical thinking and some ability to program and familiarity with a tool like R, and maybe some statistics. And so they're really pulling from a lot of different disciplines. I have a friend who is a music PhD who's moving into data science, but he had a passion for kind of critical thinking and programming. And so it worked, right? So I think actually you're in a great position for doing that.
Mm-hmm. Okay.
And
go ahead.
Oh, and I'm getting some of the questions on internships, the same idea. Like if you find something where you want to develop a skill and you see an internship in that area, you should definitely pursue that, and just really highlight that you're willing and able to learn what you need to do for the internship, and use your background experience as evidence for that.
Absolutely. Another interesting question is this kind of the question of the interpersonal skills. We realize that that's important. We also realize that, a lot of employers don't view that as trainable. I think the quote I remember hearing from another career coach is that he's heard employers say they hire for attitude and train for skills. So I thought that was an interesting.
That's very consistent.
Yeah.
Very consistent with what we see. Yeah.
But if one wants to actually highlight their interpersonal skills on a resume, is there a recommended way to do that, or in the interview process?
Yeah, okay, so
some examples.
Yeah, so in terms of like the broad look at our data, says that there's not like one credential that people will look to as like evidence that you can communicate well. So like on a credential end, like stuff you can list on your resume, it's kind of tough. However, like if you've done a co-op or some other extended research position, I think that shows like, if you did it successfully, right, it shows kind of a broad suite of things, including collaboration and teamwork coming into play. On the other hand, the interview process is where a lot of the communication skills. So if you get that face-to-face or that phone interview, that's really where to kind of let your communication skills shine.
And we had another question come up about the engineering interview they went on being very technical. Even though they ask you to do technical things, a lot of what they're looking for is your reaction to a challenging problem and your ability to communicate with them. So they're doing two things when they interview you, and a lot of the under the surface part is that interpersonal aspect.
Yeah, and that may depend a little bit. Like if you go into a company that has like a very, very well-defined degree that aligns with it, so like you go into you're looking for a job at a company that does mechanical engineering, and pretty much like every job is mechanical engineer. That's a little bit tougher. On the other hand, we see a lot of physics majors going into a whole bunch of engineering labeled jobs, where there are things like process engineer,
metrology.
Or metrology engineer or laser engineer. And people did not get degrees in lasers, metrology, and processes. They just got, they just had some general kind of background. And so I think those things will tend to be a little more flexible on the exact kind of content knowledge background that comes in.
For the resume itself, another thing you can do though is, like Ben was saying, those really specific examples of projects you've done maybe with teams, is you can add words that emphasize the communication, like I collaborated with interdisciplinary diverse teams in these specific areas, or with these people, or we worked with a client. Like, so add those details that you might not think are necessarily the technical side of that experience you're highlighting on your resume, but would add some subtle information about who you worked with on the project or how you worked with them on the project.
Yeah. So, okay. I have to say that unfortunately we are out of a time for the quote official webinar. But, for those who want to stick around, we'll continue the discussion for maybe about 5-10 minutes after this. But I do want to make a few announcements real quick. If you want to stick around, that's fine. For those who are signing off now, we do welcome you to follow up with the speakers. You can send an email to webinars@aps.org and we can forward your questions. Also, we do have a record of questions that were asked in the session. Both a recording of the video and slides of the presentation will be made available on that main webinar homepage on the APS website, which you should be directed to at the end of the presentation. It'll take us about 24 hours to get that video up, so please be patient. Also, if as you registered, you will also receive an email with the link to the recording. Lastly, in order to help us continue to develop quality webinar presentations, we would really appreciate it if, as you sign off today, you take a moment to complete a very short survey. It's 4 questions, but we really would appreciate your feedback. All right, and thanks a lot. We'll see you next time.
Thank you.
Yeah, thank you.
Okay, great. So, Anne and Ben, some additional questions. One of the questions that was asked that I thought was interesting is that we focused on undergraduates, and would any of this be different for those with graduate degrees?
So I think the interesting thing is the bulk of it is pretty applicable. So I was doing a recent set of interviews with companies doing integrated photonics. So it's like, cutting edge applications of kind of like computer chip fabrication techniques, but to actually guide light on a chip. And the idea is to like lower the cost and miniaturize a lot of optical systems. Right now, a lot of the positions out there are for PhD level people. And when we ask them about the things they're looking for in those PhDs, they're looking for good communicators. They're looking for people that can take initiative on projects. They're looking for people that can design and troubleshoot devices.
They might want you to have a little more of the big picture of how what you're doing fits in. I think that's the only kind of difference that we've seen is when you get to the PhD level, you really need to understand the broader implications and the fit of the task that you're doing.
Yeah.
I think that would be the only additional thing maybe from what I've seen.
I think it probably opens up more research and development type jobs and less that might be labeled as engineer. I'll leave it there. So.
Yeah, lots of similarities though.
Yeah, I just want to add that what you said is very consistent with my experience as well, looking at different kind of careers and what employers are looking for. I've often heard it said that at the bachelor's level, companies are going to be looking primarily for people who bring technical skills to the table, and in addition to all of the kind of things that you talked about that are very important, but they might be doing technical work. They won't necessarily be doing scientific research. That's going to be a thing that's much more likely to be available to someone who's working in a company with a PhD, for example. That said, depending on whether or not it's a small company, some smaller companies that are kind of startups and don't have a lot of internal hierarchy, there's a lot more upward mobility for people with bachelor's degrees. They could actually start in a research scientist position if they're really good at doing experimental work. I think that's a good way to characterize the difference between what you can expect with a bachelor's degree and with a graduate degree. But I also agree with you that a lot of the skills that you've talked about specifically are across the board relevant. So, yeah. Okay, so there was another question. If research experience is regarded as highly as an internship or co-op.
Yeah, I guess that's the full question. Is it?
Yeah,
it is. It just doesn't give you as much of an insight into like what you would be doing if you went into industry, but in terms of the skills you're learning, I think it's very valuable.
Yeah, I mean, I think clearly for physics majors, there's probably going to be a lot more opportunities to access undergraduate research experiences.
Early, do it early.
Yeah, early is good for sure, because you'd like to have that experience before you start applying for other things like a co-op or a job, or certainly graduate school. So you want to do it before senior year, and then I guess the other thing that could be said there is that probably the biggest difference between the co-op and the undergrad research is that undergrad research, the way it's typically done, just tends to be a little bit more individualistic. Like you are kind of focused on your one small thing. Oftentimes, you might not be part of a bigger collaboration, or at least it's not as collaborative as the work you might be doing in industry. And so I think, just kind of recognizing that might be one of the main differences, but many of the other things are very similar.
The problem solving is there.
Yeah, you still will need to ask questions, and you still will need to collaborate. It's just, not quite as heavy of a feature the way most undergraduate research is structured.
Right.
So.
And one other thing I'll add too, though, is that if your intention is to kind of go outside of the academic realm, like you're sure about that, you want to kind of, that you're bound for kind of a private sector trajectory, the network, the opportunity, like going into a co-op or an internship, obviously gives you contact with more individuals who can actually help you later in that particular path. So beyond the skills and kind of experience that you have, a co-op and an internship will definitely enhance your network outside of like your advisor or your research group in the university.
Yep. Yeah.
And if you're worried, I mean, obviously all of these things take a lot of time, but you could even get involved in like a single day project where you get some communication skills. Or I see a question about like, you're worried it'll hurt your GPA to go and do some undergraduate research. Well, there's some, you can ask professors if there's a research project, you could even just volunteer, like an hour a week or sometime over your summer. Or even another break just to get some experience. So I think there's like a variety of levels of involvement you can have, because obviously you do want, your courses and your grades to stay up, and you want to be learning from those, but just try to look for other opportunities, or even within the courses, ways to learn some of these other skills and leverage those.
Yep. Okay, another question that we have is about shadowing people. This is kind of, related, it's related to our conversation, but do you have any specific advice on how to actually do that, how to pursue that, how to get in contact with people so that you can kind of get a sense of what they do?
So I guess one, potential route for that would be to try to get involved in some professional community. So like if locally, optics and photonics is big in Rochester where we're at. And there are, student chapters of the professional societies like Optical Society and SPIE. And so getting involved in those, because oftentimes through those organizations, there's ways to meet people in different companies. A lot of companies are willing to set up tours. If you can go on a tour of a company, do it, right? Then you'll meet some people there. And that's the kind of opportunity that if you ask like, hey, could I do a informational interview, or could I shadow someone at the company for a day? It's not a guaranteed yes, but it shows that you're quite interested, and they're probably looking to hire some new people. And so, that's the kind of, but I think it is about kind of building that network and building your opportunities to kind of just meet other people.
It's harder in industry than in academia to find people's emails online. and their contact information. So one thing you can actually do is reach out even to a secretary or the main contact of that clients use for the company, and just send an email saying, you know, I'm really interested in learning more about your company. I'm a student. Do you have anyone who'd be willing to talk with me on the phone, or that I could, you know, meet briefly? Just kind of give them some options of how involved, and let them connect you to the right person. Because in college, we can just like look up our professors online and then we find their emails. But in industry, it's harder to find the right person that you would really want to be interviewing or learning or shadowing from. So you can rely on like the main contact information for a particular company that you're interested. Do your background research, really understand what they're doing, and try to get connected to a person who maybe has a little more time to show you around, or answer some questions, even by email, just as a way in the door.
And if I may add to that, another piece of advice that I have is you definitely need to take advantage of things like LinkedIn. LinkedIn is an incredible resource.
That's where you can find the contact information.
Well, not necessarily, actually. No, you can't. They've recently changed policies so that that's less obvious.
There goes my hopes.
But I can give you advice. So the thing that's amazing about LinkedIn is if you do a search on a company and you make sure that first and second degree connections are checked in the search bar, it will tell you exactly who your second degree connections are in that company. So what is a second degree connection? The first degree are people you know. Second degree are people that they know. And you know who you know, but you don't know who they know. And so if you search on that company and it'll give you this listing of all the second degree contacts that you have, it's usually a very large number of people. It'll be surprising. And if you find someone who looks like they're a very interesting person that you want to talk to, do an informational interview with, you click on your shared connection and it tells you who your mutual contact is. And then all you have to do is email that person and say, hey, I noticed you're connected to so-and-so. Would you be able to give me an introduction? And that's a great way to kind of get a targeted access to a specific person in a company. So I'm actually going to respond to your question with a link to a chapter about informational interviews and about how to get those that's on the APS Careers website.
Hey, Crystal, just to clarify, is that through the LinkedIn mail or is it actually email that you're sending?
Yes, great question. I would actually recommend email because, again, you're using LinkedIn to find out who your shared connection is, not necessarily to actually do the messaging because, again, the messaging can be kind of annoying through LinkedIn and not everybody checks their LinkedIn message, but it does tell you who your shared connection is. And usually the contact information for a first degree connection shows up. So even if you don't have that person's email address, if they're a first degree connection for you, that information will be there. The email address does not show up if it's anything more remote than a first degree connection.
Yeah.
Yeah. So that's why email is the best bet, I think. Okay, maybe one more question. I think maybe we have just a little bit of time. So there was a question about people who have a theoretical PhD, like a theoretical physics background. Are there any, a lot of the stuff we talk about, technical skills, I think is oriented towards maybe experimental, hands-on kind of approaches. Do you have any advice for somebody who's got more of a theory background?
Yeah, I mean, I do think, that some of the jobs that require computational modeling, programming, things that involve, like data analytics, yeah, maybe like systems thinking, where you're kind of trying to understand stuff on a higher level and maybe not doing the nitty-gritty
or automating
kind of
systems,
working.
computation.
Yeah, potentially there are a number of jobs potentially that involve automating certain kinds of systems. I mean, I think, you would want to leverage, some computational skills, depending on the theory project, there may or may not have been interaction with a lot of data, but it's the kind of thing, if you can do some programming, you can probably also kind of study on the side some data analysis and data science kinds of skills. Or if you just want to kind of go a modeling route, there are a lot of things that are more just like mathematical modeling, applied math,
design engineer
type positions. Yeah. So.
To get the other skills, though, just make sure you're really figuring out how to communicate, because even the people coming in with theoretical backgrounds that go into these companies in modeling, they still need to be able to work with other divisions well. And so you need to be ready for how to explain and talk and interact and ask questions of people with other backgrounds from the theoretical physics background.
Yeah, I mean, one quick example, there was a company that was looking that hires some people that have really advanced kind of PhD level experiences simulating, a particular kind of physical system. And, the company made software tools that do kind of simulations for engineers. But they needed some people more or less like physicists who had a very advanced kind of theoretical and computational understanding to actually develop kind of the under the hood models that work in those software tools. And so that was an example of a place where like a kind of a theory / computational PhD really would be a kind of an ideal fit.
Yeah. Okay, great. All right. Well, thanks again, Anne and Ben. I think this is probably time to wrap up. I really appreciate you all taking the extra time to go through some of these questions. And again, I'll remind everybody to please, as you exit, fill out the survey. As I said, the recording will be sent to you of this presentation, and you can also get it from the main webinar webpage. And that's it. Thanks again for everybody for coming. Thank you.
Thanks, everyone.
Yeah, we hope you'll join us again next time. American Physical Society, copyright 2018, all rights reserved.